Anything you can do, I can do better. I can do anything better than you. No, you can't. Yes, I can. No, you can't. Yes, I can. No, actually, I think, yeah, maybe, yeah, you can, because now you've learned everything you were supposed to know. Now the class is over, let's talk about the map of everything we've done in here. Our first question is always, what are we testing? Is it a mean, meaning we're working with numerical data, or are we talking categorical data and we're looking at proportions? And then we're going to ask ourselves, how many do we have? One mean, two means, or lots of means, which we did with regression, where those means followed a line. With proportions, we have one proportion, two proportions, or lots of proportions, which can be written in some sort of table. For all of these, you have to deal with the question of, is it even valid to do this hypothesis test? For means, it either will tell you that it's normal, or your sample size will be over 30. For two samples, it would be both of them over 30. Unless we're talking about regression, where you look at those residual plots, and you can see all 1, 2, 3, 4, 5 of those assumptions are met if it's a good residual plot. If you do see a pattern in that residual plot and it asks you to do the test, still do the regression test, because what looks like a clump or a swerve to you might not to somebody else. So there will be specific test questions saying, which assumption do you think might be violated, and then go ahead and do it anyway. For proportions, you need NP greater than 15 and N1 minus P greater than 15. For two proportions, it's the same for both groups. I've had to write so much that it just looks like a blur or marker. But basically 15 yeses and nos in both groups. If we're talking about a table which leads us to the chi-squared testing, then you need all the expected values to be greater than 5. And that's true for both the chi-squared tests that we have studied since the last exam. Now, in the regression case, you'll do it even if the residuals look bad. But for all the others, if it doesn't meet the condition, the answer is cannot do. And you'll want to watch for those on the exam. For one sample mean, we're going to ask ourselves if we know sigma. And let me try to squish it on this side of the board. If we do, there's our first hypothesis test with z-score and the sigma. And the confidence interval is the same equation but worked around backwards. It's really important that you feel comfortable with this, because if you don't know sigma, the t-test is very similar. You just have to watch those degrees of freedom and make sure you're using S. And I realize you'll get the same answer, but if you keep straight what you're doing, you'll know whether it's Z or T. And that's mu belongs to equals isn't quite right because it's a range, but if that confuses you, just think of it like equals. If you're okay with that, then moving to the two-sample test, looking at matched pairs is super easy because it's the same equation. Mu changes to 0 specifically, and we use mu d when we talk about the parameter, but otherwise we put little d's to remind ourselves we're talking about the difference. It's really the same deal. Now for the two-sample independent test, it looks a lot nastier until you realize it's just double of everything. Where we used to have x bar, now we have the difference of two x bars. It's still 0 for the same reason. We're testing two groups. And then we have s over the square root of n for the first group, and the second group, squared invariances, added and square rooted. If you get that concept, this equation starts to look just like the others. And the confidence interval is merely a solution of the others, except I forgot the belongs to. It's always a challenge to try to fit everything on the board. The map's just not the right size. For proportions, after we know the assumptions have been met, we can go straight to the z-test for p hat. And here, that square root of p hat 1 minus p hat over n, that is a little new, but the confidence interval is still solved the same way. And when we talk about two proportions, they work the same way two means did. The difference in the proportions and the square root of, here there's a p bar. How do we find that p bar? It's the pooled. You take the yeses from both groups divided by the sample size from both groups. And confidence interval, I did remember to write my p1, p2 belongs to here, even though maybe it doesn't matter, but it's my goal to see if I can fit the map on my board for like the first time ever. And here it's not p-bar, it is the individual proportion 1 and proportion 2 that are separated, which makes it exactly the way this two-sample test worked. Now, for the multiple proportions, which leads us to our chi-squared testing, you want to ask yourself, do I know the expected values? That's the same as saying, is there only one row of data? Because we talked about the goodness of fit where there's only one row, or the test of independence where there's multiple rows. And for the test of independence, we calculate those expected values as row total, column total, over the table total, and the degrees of freedom would be row minus 1, column minus 1. If we only had one row, if we did know those expected values from the beginning, then our degrees of freedom would just be k minus 1. which then leads us to our chi-square test. Both of them use the same observed minus expected squared over expected. So that fleshes out all this except for regression. We need our hypothesis test and confidence interval, which follows the same pattern we've been using. Statistic minus parameter, which we're hypothesizing is 0, over the standard error, and the computer does that whole calculation for you, and the confidence interval is solved that way. So your goal is to be able to see all these different formulas as simply variations of the same original formula, and use this map to follow through and say, what type of test do I have, and what kind of parameter do I need? And I'm super proud I fit it on my board. That's like the first time ever. Usually some formula gets all scrunched at the end. But this is hard to put on a paper. If any of you out there make a good map of this on a study sheet, let me have it and I can share it with the class. I'll share you some links that I've had in the past, but it's very few people who offer something.